Dobar dan, zdravo svima. Neki me znaju, neki me ne znaju. Ja sam Slova Marković iz Registra nacionalnog internet domena Srbije. I želim da vas pozdravim sve na ovu radionicu o IPv6-u koji organizujemo u saradnji sa ISOC-om i puno dobre volje naših današnjih predavača. Tu su sa nama Jordi Martínez i Jan Žorž. Ja ću nam se pridružiti, mislim da sređuje nešto oko uspostavljanja IPv6 sa internet providerom i tako dalje. Ali mislim da je Jordi već navestio sve što treba, tako da smo spremni tehnički. I samo bih još hteo da vam se zahvalim za učešće na ovoj radionici, a pogledam i na učešću na sutrašnjem skupu RSNO konferenciji. Tako da, pošto znam da se dosta vas prijavilo na učešću na RSNO konferenciji, tako da se vidimo u sutra. Eto, Jordi.
Okay, so this is for the camera, not for, okay, yeah, because I was not hearing the feedback. Let me quickly introduce myself. I am Jordi Palet. I work for a Spanish company. We have been doing IPv6 since '99, so it's a long history on this. We have done either workshops or training ISPs or organizations and doing consultancy in already more than 125 countries in the world. So we have, again, a lot of experience on this. When they asked me to participate in the tomorrow panel, I said, okay, why not taking the opportunity I am here, organize an open workshop? So that was the idea. I understand that most of the people that is here is from ISPs, that's right? Who is not from an ISP? Maybe you want to tell which kind of organization? ISPs, everybody, or not? Universities, enterprises, government? Okay, more or less, mixed, but majority ISPs, that's what I understood. Let me explain a small difficulty that we got, and we get busy during the last 3 hours trying to figure out. When I do this kind of workshops, I try to do them as much interactive as possible, so it's not just me speaking, but you being able to test something. So we asked about the configuration of the network and so on, and when we arrived here, we tried to configure it, but not everything is working. For example, the access points, the ubiquity are filtering IPv6. So instead of using the ubiquity, you will be using this small $10 box from China that is actually doing IPv6 for you. We will talk about that later. I will explain what is in this box. Before we start, I am very flexible on the contents. There is what I believe a very important part, which is targeted for the last part after the coffee break, which I am going to teach you how we are going to have in the future the networks in both the ISPs and the government, universities, and enterprise networks, which is IPv6 only, okay? We will not have any more IPv4, and that's the way we should think in the long term. That will be after the coffee break. Now, depending on your actual knowledge on IPv6, the first part can be one way or the other. So I need your input now about what IPv6 knowledge you have. For example, everybody here, of course, has IPv4 knowledge. I give that as for sure. But regarding IPv6, everybody knows that IPv6 addresses are, for example, hexadecimal, that there are different types of addresses than what we have in IPv4, or the majority don't know that. So you say?
The majority wouldn't know that.
Will know that. So we will skip that part, because that's very basic, okay? Please raise your hand, those of you that already have done some basic thing with IPv6, like ping, trace route in an IPv6 lab. Everybody done that? Almost. So that means that even if we can do that, because we have IPv6 connectivity here, we will do that very, very quickly, okay? So what I am going to do then is let me think. Okay, I will skip the basic part. Let me close because I have 10 presentations open here to choose. So I will skip the basic part. That don't mean that during all the afternoon, whatever question you have, even if it's not the topic I am talking in that moment, just raise your hand and ask me at any time. Okay, so if you need any clarification, just let me know. I will skip. Okay, so I think I will go straight to the most difficult part of IPv6, which is transition. Okay? And then after transition, we can do some testing here in our network until the coffee break. Okay, so when we talk about IPv6, many people talk about migration. Migration don't exist in IPv6. Okay, there is not in ITF. Everybody knows what is ITF. Yeah. So basically, ITF is the organization that developed the internet standards. It's a volunteer work. Nobody gets paid for that, and you donate your time and you contribute writing documents to define how the protocols work. So when we started long time ago, I think it was already 30 years ago, thinking in the need of IPv6 because we had the clear vision that IPv4 will run out, we conceived IPv6 in such a way that we tried to avoid breaking IPv4. So the basic idea was, let's have IPv4. This is one side. Let's have IPv6. If we put that in a how you say, a weight, okay? The IPv4 traffic today will have the bigger weight, right? Most of the traffic in internet today is IPv4, and IPv6 is like here. So what we want to do is both protocols to coexist in such a way that the balance, the way of the traffic will change over the time. So today we have 100% of the traffic in IPv4, 0% in IPv6, and that's going to change. That's what we call coexistence. Both protocols live together for some time. And transition. The difference between transition and migration is what you do when you have a computer with Windows XP, and you install on top of XP, deleting XP, Windows 10. That's a migration. You don't keep both of them. Okay? You have one, you install the other one, but the first one is deleted. We cannot do that in IPv4. We cannot do that in internet because it will mean you will lose connectivity. If you just install IPv6, we will lose connectivity with websites, for example, or services that today only work with IPv4. Okay, so that's the main thing here. We don't want to break the network, or we want to avoid as much as possible to break things. Some things will be broken, for sure, especially because some people is getting slow in deploying IPv6. So when we were thinking on this in ITF, we defined different ways to deploy this transition mechanism. And in fact, we developed basically 3 strategies, or 3 types of transition mechanisms. The basic idea was, let's have dual stack. Dual stack means IPv4 and IPv6 in every interface. What happens? That because we have been so slow deploying IPv6, dual stack is impossible because we don't have enough of IPv4 addresses to keep running. Okay? So if we have deployed IPv6 10 years ago, today everybody will be dual stack, or in fact will be IPv6 only, but we have not succeeded to do that. So dual stack, which was the best way to avoid breaking things, today is not possible. How dual stack works? Dual stack works basically the same way we had other protocols before, like IPX, AppleTalk, and many others, and we put on top of them IPv4. So what happens here is that we have a decision based on DNS. If you have a web server that today has an IPv4 address, which is an A record, and you want to have also IPv6 connectivity into that web server, in addition to provide a link with IPv6 connectivity, you need to define what we call the quad A record, which is the container of the IPv6 address. Okay? So what happens is, now that we have an A record and a quad A record for the web server, the client will find that the web server is available in both v4 and v6. And in theory, it should give preference to v6. That's the reason the weight will change. Because as more and more clients and servers have IPv6, there will be more and more IPv6 traffic and less IPv4 traffic. Everybody understand that? Please, whatever question you have, if I speak too fast or too slow, or I am saying something stupid, just let me know. Okay? Interrupt me at any time. So this is the basic idea about dual stack. Okay? So this will be an example of a dual stack. I think I have a pointer here somewhere. Let me see if it works. Which one? Is that one? No? Whatever. We can do without the pointer. Maybe the battery is dead.
Maybe.
Oh, that's it. That's it. Okay. The switch was off, and I didn't realize that. So this will be a dual stack machine, and having dual stack, many people believes means the stack, the code of the stack is double. Actually not, because as you can see here, TCP and UDP is almost the same for v4 and v6. So typically today, a well-optimized stack takes only 30 kilobytes. Okay, so it's really, really tiny stack. If we have dual stack, it's not 30 plus 30. It's maybe 30 plus 10% more only. Okay?
It works.
It works, which the... Okay.
If you connect to Milutin, you will have IPv6.
Okay. So we have two ways now.
Exactly.
So the point here is, if we have dual stack, and we have at certain point IPv6 only host, like for example Internet of Things devices that have only IPv6, you are able to connect to them, right? And you have all devices, for example, a weather temperature or meter in Alaska, which is IPv4 only, you still can connect to that device. So ideal situation, let's have dual stack at every host. What happens here is that having dual stack at every host in a computer or in a router is not a problem, because it has enough memory, enough CPU, whatever. But let's think in cellular phones. Cellular phones having dual stack, it consumes too much resources. Okay? For example, having IPv4 behind a NAT in a cellular network, it means that every 30 seconds you need to have what we call the keep alive packets. So that means, hey, NATbox, keep the ports open. I am still here. After 30 minutes, again, and so on. So that means something very simple for users, which is battery consumption. So something so silly like that makes interesting for cellular phone vendors to kill IPv4 as soon as possible. Okay? Now, what is the following approach? The following approach is what we call tunnels. And there are many ways to do tunnels. In fact, the concept of tunnel is something that most of you probably are using, because most of you probably have MPLS in your network, so it's a kind of tunneling. Or you are using at some point VPNs, right? So it's the same. The difference is that instead of transporting IPv4 in IPv4, we are transporting IPv6 in IPv4 or IPv4 in IPv6, okay? So we can have both choices, or even more complex choices, like, for example, I have an IPv4 or an IPv6 network which is unicast, and I can transport in that unicast traffic, in that unicast network, multicast traffic, okay? So all the possibilities are there available. We will talk later about different ways of doing tunnelings, and we will explain, in fact, how we do the tunneling, the connection to IPv6 here by means of a tunnel. So this will be the most simple way to understand a tunnel. A tunnel is nothing else than a point-to-point link. You all know what is a point-to-point link. So you need to set up a connection between A and B and B and A, because it needs to be bidirectional, okay? So basically in this picture you have a destination network, we have internet or an ISP that is only IPv4, but you want to use IPv6 end-to-end. So for that you have a router doing a tunnel to the other router, and again this is a point-to-point link in both directions, and we can do that also from a computer. It's not necessarily just a router, okay? So that's the most basic and simple way of transporting IPv6 on top of IPv4. What that means, we put the IPv6 packets inside an IPv4 header, okay? There is an obvious consequence on that, is that the IPv4 header takes 20 bytes. So you, instead of having, for example, 1,500 bytes, now you have, for IPv6, 1,480. Okay? That's one typical consideration. And this consideration is very relevant because how many of you here filter ICMP in your network? Nobody's doing that? There are many ISPs that filter ICMP. In IPv6, you should not filter ICMP, because the way to discover the size of the packets that you are able to send through a path is by means of ICMP signaling, okay? ICMP v6, actually, okay? So that's an important point. Now, there are other ways to transport or to encapsulate in a tunnel IPv6. The one that I just mentioned is this one, IPv6 on top of IPv4. This is called protocol 41, okay? It's also called 6 in 4. It's not the port number, it's the protocol number. So it's, instead of being TCP or UDP or whatever, it's a protocol with the number 41. There is another way which is using GRE, which I believe it's for protocol 47, if I am not mistaken. So you can do the same. The difference between 6 in 4 here and GRE is that 6 in 4, if the tunnel gets broken, you only will realize that when you try to transmit data, because it will not reach the destination. While in GRE, there is a control channel that is going to tell you that the tunnel is broken, even if there is not actual data being forwarded, okay? And then there is another way, and again, this is only 3 examples, the most common ones. There is another way, which is UDP. Why transporting IPv6 on top of UDP? To get rid of NAT boxes. Many people believe NAT boxes are security. I am sure you all know that that's not the case, but there is many people that still think NAT is good, we cannot go to IPv6 because we don't have NAT in IPv6. NAT is providing security. This is not true. And the way to prove that is that you can make a hole in a router, even with NAT, by means of UDP. If you know how to set up that, you will be able to traverse the NAT, okay? There are many, many, many protocols for doing this kind of tunnelings. In fact, one of the, let's say, bad things that we did in IETF was probably developing too many transition mechanisms. We did that because we expected that every scenario will need a more specific transition mechanism, and also because the evolution of the time. Okay, so depending on what is the evolution of the network and the penetration of different topologies or ways of doing internet and connecting things, we needed new ways to do that. But at the end, we are confusing ISPs. We are confusing ISPs because most of these transition mechanisms today are not so much useful, okay? Especially, and we will see it at the end of the presentation, because we get rid of already IPv4 addresses. We don't have more IPv4 addresses, so we cannot rely on mechanisms that depend on IPv4. In fact, what we tend to do today is deploying IPv6 networks and tunneling IPv4 on top of them. Okay, so the other way around.
So last time I counted, we had 23 transition mechanisms.
I counted more than that.
Yeah?
Yeah, I think I counted almost 47 or so, but many of them are like stupid things.
23
Yeah.
major of them, and now you
Yeah.
as an ISP,
How to choose? How to choose? That's the point. Well, the target of this presentation is to tell you what is my vision about how to choose that, okay? And what I will say, don't use anymore this one. So, tunnel details. I think I explained this already. Yeah, it's nothing new here. It's just a point-to-point link. We set up a connection from A to B and from B to A, so we can have bidirectional traffic on that tunnel, okay?
This is what we set up here on the local microtic.
Exactly. So what we have done here is, if you look at this tunneling mechanism, basically it's a point-to-point configured manually. So now, if you have 500 customers, are you ready to set up 500 tunnels for all your customers? Well, maybe for 500, maybe, but if you have 500,000 of customers, will you do that? Definitively not. So we invented what we call tunnel broker. Tunnel broker basically is having a web server, which is in the picture. Where is the tunnel broker? Okay, I think this picture is missing something, but whatever. The idea is that instead of configure manually this router from the ISP, you have a web interface to be able to automatically configure that. And in the worst case, the only thing that needs to be configured is the customer side, but the ISP side is configured automatically. Okay? That's the idea of a tunnel broker. There was an attempt to make tunnel broker like the most prominent transition mechanism. And there have been a couple of companies at least that even make appliances to do tunnel brokers automatically. But today, it's not really an option. Tunnel broker is for something like what we have done here today. There is a public service from an operator which is called Hurricane Electric. And Hurricane Electric provides a free service to give you a /48 if you want it. By default, it gives you a /64. So you can configure your IPv6 network if your ISP is not providing already the service. Okay? So that's a very simple way to do this thing. And it took us basically 5 minutes. The only problem we had is that the ubiquity were filtering IPv6, and we would get mess of what was going on.
Yes, so we figured out what was going on. It was not IGMP snooping, but if you apply the guest policies to a network to isolate the SSID from the other one, it stops forwarding anything IPv6.
Okay, that has an explanation.
And what is worse, there were reports to YubiKeepi that this is a bug, and YubiKeepi said, no, it's not a bug, it's a feature.
What happens, I understand what happens here. What happens is Ubiquiti want to make by default a policy in the sense that you cannot see my traffic and vice versa. Okay? So you can only talk to the router, but not the rest of the people in the room. That's the policy. The problem is that IPv6 is based on link local multicast to being set up. So if link local multicast is not working, you will not be able to have IPv6 working automatically. You can do some tricks to make it working manually, but it's not what you want to do.
For client isolation, I guess. Not
it's for client isolation, but the way Ubiquiti is doing is wrong. Because it's good for IPv4, but it's actually breaking IPv6. There are alternative ways to do the same without breaking IPv6. To be honest, I have seen that in many access points. So it's not just Ubiquiti fault. Many vendors have this problem. Okay? So this is something important to remember. To get IPv6 working in a network, you need to make sure that link local multicast works. Okay? In a shared network, you need to have link local multicast working. It's something different than what I have in the slides, but gives you an idea of the difficulties you have when you set up IPv6. Okay. Any question about what is a tunnel broker or a tunnel in general, or is clear? Okay, so keep going. There was another protocol, and I said there was because it's not anymore used, which we call it 624. 624 is based also in 6-in-4 encapsulation, so it's also protocol 41. The difference is that in this case, 624 is expected to have a public IPv4 address for its router. So if this router gets a public IPv4 address, and also this router gets another one, 624 is using a special prefix, which is the IPv6 prefix 2002::/16, and 2002/16, obviously 16 bits. The /16 is telling us that it's 16 bits. So what happens if after that you have an IPv4 address? How many bits is an IPv4 address? 32. 32 plus 16 is 48 bits. So it means that with this mechanism, totally automatically, you don't need to configure anything. You get a /48. Once you get the /48, it means this network and this network can talk together, peer-to-peer, with IPv6. Okay? That's very good for peer-to-peer communication. Now, if you want to talk to Google, you need to have what we call the 6-to-4 relay. And the 6-to-4 relay, that's the difficulty, is guessed by means of anycast. And anycast is not the best way sometimes to find these things, because it can happen that you are using a relay instead of this city, you may be discovering a relay in the other side of the world. So your traffic is going to go to Japan and coming back. Okay? So I will say today there is no reason to use 6-to-4 anymore. But still there are many routers in the market that come with 6-to-4 enabled by default, which if you are an ISP and you have customers and you don't provide IPv6 service, it means the quality of service that they are getting is going poor. Okay? So it's better in that case that you actually deploy a 6-to-4 relay internal to your network instead of doing nothing. If you cannot do native IPv6 service to your customers yet. There is a similar concept to 6-to-4, and let me tell you the story of this protocol. The gentleman that developed this protocol, Christian Utema, he's a French guy, but he has been working for many years in Seattle for Microsoft. Okay? So he come to the ATF with an internet draft. I don't know if you know this history. He come to the internet with a draft which was called shipworm. Shipworm is the worm that eat the wood of the ships. Okay? Just because the name of the protocol, the people didn't like the idea. Most of the people even didn't read the document. They just said, no, we cannot have a protocol that is called worm, whatever worm. So he, in France, and in many Latin languages or speaking languages in Europe, we still teach in the school Latin. And here remember that shipworm in Latin is Teredo navalis. It's the same. So he cut the word, he used it just Teredo, and he submitted again the document to ITF, and then it was accepted. Of course, because 50% of the people in ITF don't speak Latin. Okay? So you knew this history, Jan?
No.
No? You were not still contributing to ITF at that time. Okay, so what Teredo is doing is doing holes in the NAT boxes to transport IPv6 as UDP traffic. So when I said a few slides ago, NAT is not security, this is the demonstration. Okay? You can have a secure network with IPv4, but you can make a hole in the NAT box using Teredo. The concept is very, very similar to the one I just mentioned, 624. The difference here is you need to configure the box, what we call a Teredo server. The Teredo server has 2 consecutive IPv4 addresses. So when a host inside a NAT box wants to get an IPv6 address with Teredo, he will ask the Teredo server, hey, I want to go live with IPv6. And the Teredo server, using these 2 consecutive IPv4 addresses, will find the way to make the hole in the NAT box. Okay? So if you are a hacker and you want to make holes, you just need to buy an IP range that has several consecutive IPv4 addresses. That's it. Fortunately for the hackers, typically it's easier than that. They just send web pages with whatever to hack your network. But this is a very simple way to hack a network, and the people still believe NAT is security. Okay? So clearly this is not.
I will tell you another way, but it has nothing to do with IPv6. But it's interesting. So
it's interesting, yeah.
We'll talk about it later.
Okay. Now, after we have developed all these transition mechanisms, we started considering, especially thinking in the cellular phones, but not only, that we need to find a better way that fits in every scenario. So the idea was, instead of having 20 transition mechanisms, one for each scenario, let's have like one shirt for all sizes. Okay? You have this expression here as well, I guess. So the idea was one size fits all. So we started to work in this new working group in ITF that we call Softwires, and we had several candidate ideas. I designed one protocol, somebody else designed another one. There was something like 4 different proposals, and then Cisco come to the table and say, hey, we don't need anything new. We have L2TP, and we can adapt L2TP to do the same. So this is what Softwires is doing. Softwires is using L2TP and adding what we call Softwires header to transport either IPv6 in IPv4, or IPv4 in IPv6, or IPv6 in IPv6 for multicast traffic over unicast traffic, and also the same for IPv4 in IPv4. Okay? So for those that don't have knowledge about L2TP, basically is having a data channel and a control channel. That's it, basically. And it's a kind of set of headers to decide how you do the traffic. The main difference between L2TP version 2 and L2TP version 3 is that L2TP version 2 mandatorily needs the UDP header, okay? While in version 3, you can skip that. This will be an idea of how it will work. You have a CPE, a small router, with a customer LAN, and the CPE is what we call the Softwires initiator. So it's like the one that is calling to the L2TP server. And then you have the L2TP server, which we call Softwires concentrator, And this is exactly the same if you have already L2TP deployment in your network, but instead of for virtual private networks, for transporting IPv6 on top of IPv4 or IPv4 on top of IPv6. Okay? So that was the idea of soft wires. What happened is that soft wires actually didn't succeed in the market. There was not too much penetration, but as a consequence of soft wires, we defined a set of transition mechanisms that basically are optimizations to soft wires. Okay? Another transition mechanism. If you still have IPv4 addresses, I will not suggest this one today, but just so you keep in your mind this wording, 6RD is doing something similar to 624, but is using, instead of any cast to any relays, is using your own system of relays in your network, which they are called 6RD gateways. Okay? This has also a very interesting history related to our friend Mark Tomsley. There is an ISP in France which is called Free, which is one of the biggest. And one of the guys in this ISP, by the way, they are people using their own set-top boxes based on Linux. They do everything by themselves. Okay? So one of the guys said, well, 624 is a nice idea, but I want to get rid of the anycast problem. So he proposed a document in ITF describing 6RD. He tried to convince me and a lot of additional people, and we said, you as well, and we said, no, this is not interesting, give up. They started implementing it, and then this guy from Cisco, Mark Tomsley, he's American, but he's married with a French, and he's living in Paris. He decided to contract a link with them without knowing that they were doing this, and then he said, oh shit, they are doing IPv6 and Cisco has not been able to solve the problem. So he asked them, hey, can I be co-author of the document with you? And he got it as a standard. Okay?
And you know what happened later in Norway? There was one ISP that wanted to implement IPv6, but their equipment, their network, access network, was not able to forward the IPv6 Ethernet packets. The DSLAMs were too old. So they basically implemented 6RD to implement IPv6, and they said, oh, but now we are running out of IPv4 addresses. So they deployed MAP-E on the top of 6RD.
We will talk later about map. So, what basically 6RD is doing is the same as 624, but it uses, instead of the 2002 prefix, which is the same for all the ISPs for 624, it uses the actual ISP prefix delegated, for example, in this region by RIPE. Okay? What is the problem with that? The problem with that is that if you go to RIPE by default, they will give you /32. If they give you /32 and then you have 32 bits for the IPv4 address, you are giving to the customer /64 only, which is broken. Because giving in IPv6 a single /64 is the worst thing you can do. Okay? A single /64 means if you have a wireless without additional /64s, you cannot have a guest wireless. So if you have, I don't know, your family pictures or your porn with your wife or whatever, your guest will be able to see that, which is not nice. Okay? So you need to provide multiples of /64 to customers, even if they are residential customers. We have a document together, which is now a RIPE 606 is the number? The pickup? 606. Yeah, I think it's 606.
Which one?
The prefixes.
Prefix delegation.
Yes. 606.
690.
690? Okay. I don't know why I keep 606. Exactly.
690.
So the idea is, by default, our belief Even in the document we relax a little bit, but our belief is it's better to give everybody /48. Everybody, never mind is residential or enterprise. If you really want to enforce a difference, then 48 for enterprises, 56 for customers. But believe me, that will break you in the future. Okay? So if you really want to follow my advice, go for 48 for everyone. It's easier. And you don't get to renumber in the future. Okay? Yeah. So what we did, and actually we did as well together, and with Mark, is we changed the RIPE policy. So by default in RIPE, instead of getting a /32, if you want, you get a /29. So you have more bits to do that correctly to the customers.
We needed 1 year for that or something.
Sorry?
We needed 1 year for
it took 1 year, yeah. Yeah.
To change from Z32
yeah.
to Z29. Yeah.
Anyway, today, if you go to RIPE and you have an addressing plan, it's not a problem to get more space. I got for the Spanish government a /26. Okay, and a /26, believe me, is really, really, really big if you want to make the numbers. So this is not a problem. You can really justify whatever is your need, and RIPE will do that. If not, come back to us and we change the policy again, if necessary.
We know people who know.
Yeah, okay. Now, one of the kind of transition mechanisms, when you want to do the break, just let me know. If not, I keep going speaking and I never stop, okay?
He could speak about this for 2 days.
2 days only, 2 weeks. 2 weeks, actually. Okay, so the third set of transition mechanisms is what we call translation. What happens basically is that we invented a translation protocol which we call it NATPT. And NATPT was meant basically for if you have a web server that is not able to support IPv6, you put in front of it, you put a box, a proxy, kind of proxy, to be able to support IPv6 on that box without changing the server. Okay? That looks like a very nice idea. And actually it's very nice if you use that only for HTTP. But if you start using that protocol for many other things, at the end it gets broken. So we decided in ITF that this protocol should not be anymore a standard. Okay? So now NATPT is not a standard, but we see in the market that the people has no more IPv4 addresses and we need to find a solution. And the only solution, we like it or not, is translation. I am against translation, but there is no other way to do the things when you don't have any more IPv4 addresses. Translation will almost always break something. How much important is that what gets broken or not? That's the thing that you need to decide. Okay? It may depend also on the type of customers. For example, in a cellular network, it's a very well-controlled environment. So you really can make it in such a way that you don't break anything. If somebody does an application which is doing something strange, then it's their fault. But they are not using the standards in cellular networks, which is basically using almost only HTTP and not too many else additional protocols. Okay? Now, one of the things people started to do is what we call carrier-grade NAT. Carrier-grade NAT.
Why are you swearing? Why are you swearing?
Swearing. Carrier-grade NAT is another thing that having the NAT box, in addition to the one that every customer has in his CPE, you have also a big box, a big NAT box on the ISP. So what actually happens is that with that you are artificially extending the life of IPv4. But carrier-grade NAT is not meant in principle to deploy IPv6. It's just to keep extending IPv4. What happens is that you are sharing ports you are sharing addresses among different customers. And to that, you need to decide how many ports you use for every customer. So for example, you can say, let's use 1,000 ports for every customer. Because an IP address has 75,000 ports, it means you can have 64 customers in a single IPv4 address. Now, let's suppose your neighbor, which is using the same ISP as you, is doing some criminal activity in internet. When the police need to investigate who has done that, he will need to investigate 64 people. Okay? So we have been working, for example, with Europol on this to tell them, hey, this is really bad. Don't do carrier grade NAT. It's bad for the customers, it's bad for applications, it's bad for operators, it's bad for investigations of criminal activities. So it's really a problem.
Yes, in December, 20th of December in Geneva, there is Internet Governance Forum meeting, a big one from UN, United Nations. And there is actually a panel discussion with Europol that was initiated by Europol about bad implications of carrier grade NAT and what IPv6 actually changes in this respect. And I'm one of the members of this panel discussion, and I'm really looking forward to it because I'm really glad that even Europol started basically promoting IPv6 because it makes everything much easier. So, for example, we have this Belgium case where ISPs, Internet Service Providers in Belgium, entered into a voluntary agreement with Europol and the police not to put more than 16 people behind one IPv4 address if they have a carrier grade NAT. And this actually resulted in ISPs figuring out, oh, this is not very useful, this is not very efficient. And they basically deployed IPv6 and started using IPv6 because they're running out of V4 addresses. And basically what's happening now is that Belgium has the biggest, the greatest IPv6 deployment in the world. More than 50% of traffic that comes from Belgium towards Google services is on IPv6. 50%. They reached the critical percentage. And everything works. Everybody survived. Everybody's happy. No complaints. So IPv6 is not that scary. It is just another protocol that you need to implement in your networks. And Belgium is a good example. 50%, can you imagine, of all Belgium.
I think they are already close to 60.
Yeah,
close to 60, I think.
They're closing 60%. 60% of traffic is on IPv6. So it can be done. It's not a myth. It's not just a nice story. It can be done. And when your police will figure out that you're implementing carrier grade NAT, if you're implementing carrier grade NAT, and somebody from your network hacks, I don't know, Deutsche Bank and steals 10 million euros, guess where that public IP is configured? Law works a little bit differently than in engineering mind. They will come and say, or you provide us the name of the person that stole 10 million euros, or
you have a problem.
Where was the IPv4 address that we have in our logs configured at that point in time? Oh, it's your carrier grade NAT machine in your network. Who is the owner? You are ISP. You are the owner of this machine. And this IP was configured on this interface. Yes. Give me my 10 million euros. That's how law works. If Deutsche Bank or any other bank goes and sues you, you will have to pay what one person did in your network, and you are not able to provide the details of this person. So think about it.
In addition to that, I remember when carrier grade NAT boxes were into the market, I think it was about 5 years ago, more or less, each box was costing about $1 million, each box. Now is 200,000 euros, more or less.
They come with disclaimers against manufacturer liability for the...
Exactly.
Of course, no liability to the vendor.
Because if they sue us...
You sue the vendor. No way. No way.
No.
No way.
You should sue IETF for actually making the net protocol.
And then the author of that RFC, maybe.
Daniel Karenberg.
So actually, is no way. One thing that the people don't realize also is that when you put a carrier grade NAT box, you need to put not just one, but a set of them. Also because high availability, but because each of them can handle maybe 100,000 customers, but not 1 million customers. So maybe in your network, if you have 1 million customers, you need 20 NAT boxes. So if you compare the cost of that versus deploying IPv6, actually, it makes sense in the long term to go to IPv6, not to keep going with carrier grade NAT boxes. Okay? And in addition to that, there is something else, which that carrier grade NAT boxes require what we call ALGs, application layer gateways. So for example, if they break FTP, you need to put an ALG for FTP. If they break something else, you put another ALG. As much as you start putting more and more ALGs, the performance of those boxes is going down. So maybe instead of 20 boxes, you need now 40 boxes. Okay? So it really gets something very, very complex. And because law enforcement, you need to keep the logs to avoid the situation that Jan just described. You need to keep the logs of the source address of every connection. And the systems to keep the logs, including all that, cost more than the carrier grade NAT boxes itself. So at the end, it's like a big snowball of money that you never end. Okay? So definitively, people that is trying to keep going with just IPv4 with this, it's making a wrong decision. Now, this is a way to see how carrier grade NAT works. By the way, I forgot to mention something. If you see in a document this wording, AFTR is the technical name in the RFCs for carrier grade NAT. It's Address Family Transition Router. Okay, so you will see AFTR, CGN, CGNAT, large scale NAT, which is LSN, etc. You will see many names for all the same, but definitively it's just NAT 444. Okay?
It's very simple. Just remember a very simple thing. NAT equals evil. Carrier grade NAT is carrier grade evil. Very simple.
Okay. Now, how it works? We have the NAT box in the CPE. Okay? We have the NAT functionality in the customer CPE. Before, we have here a public address. Now, with carrier grade NAT, the public address moves here. Okay? So the customers can share all the same IPv4 address in the one of the CPE. And then it means you have two levels of NAT, one level here and another level here, which means that some applications will break because many applications are designed or developed to survive one NAT level, but not two. Okay? I have suffered, while traveling, I have suffered the consequence of this. For example, a few years ago, I was doing a training in Laos, and in that country, they already ran out of addresses, the ISPs, and they were using carrier grade NAT in the ISP that provided the connectivity to my hotel. I was in the last day to pay the taxes in my government, and when I tried to make the payment, it was not working because it was not survived two NAT boxes. I put a complaint to the Spanish government, hey, you don't have IPv6, it's not my problem because the hotel has IPv6, but your IPv4 connectivity is broken. Oh, well, Google work on that, but meanwhile, you pay 150% of additional, fine for having got 1 week delay in paying your taxes. Okay? So that's an example of things that will get broken more and more when you have several levels of NAT. Here is a list, and this is only a partial list of many things that get broken with carrier grade NAT. Again, you can deploy ALGs, but not necessarily you will have enough power to apply all the LGs, or it will mean you have to apply to have more carrier NAT boxes. Look, for example, this thing here, online gaming. You know what PlayStation, Sony PlayStation is doing? When Sony detects that you have an IPv4 range in a carrier NAT box, they block it. They put it in a blacklist, and they will never delete that from the blacklist. So people that has ISPs that have many gamers, they are every few months needing to change the IPv4 addresses on the carrier NAT box until they run out, and then they need to go to the gray market to purchase IPv4 addresses. Okay, so that's an extra cost. And the bad side of this, and this is blaming Sony, is that they don't support IPv6. Because if they support IPv6, you can do that, but they still not support it. I am not a gamer, so I am not on this wall, but I know many people that is having this kind of problems. Okay, so this is an interesting history. If you have a lot of people using online gaming, sooner or later that will affect you.
And remove TV from my home. I have a Sony TV. Oh, just PlayStation.
It's only with PlayStation, up to what I know.
My kids will love it.
Yeah. Okay, so what happens is we run out already of IPv4 addresses, so it don't make any sense to keep trying to use the transition mechanisms that we have been talking up to now. Okay? So the idea is, why not deploy IPv6 only networks? If you deploy IPv6 only networks, your operational expenses, your capital expenses go low. The performance on your network, you will see later one slide about that, goes up. The efficiency of your network goes up. You are complying new RFCs. For example, one of the works that is on the kitchen in IETF is declaring IPv4 as historical. So that means that if you have hardware from a vendor and the RFCs for IPv4 are no longer standards, the vendor has no reason to keep developing IPv4 even if there are bugs. Okay? That may happen not in 1 year, maybe it will take 2, but for sure it will happen. Okay? So you need to take care of that, because at the end, if you don't start deploying IPv6 today, maybe it's too late in the future. So one of the transition mechanisms that we developed, and I talked about softwires before, because all the transition mechanisms from now on somehow are based in softwires. So DS Lite, dual stack Lite, is a way to share using tunneling and NAT the few IPv4 addresses that you have. How it works? Here is the picture, easier to see. So basically, what we have is we replace the CPEs, or we upgrade the CPEs, which for carrier NAT is not necessary, because carrier NAT, remember, is just to keep going with IPv4 forever. So you don't need to change the CPEs. But in this case, for DS Lite, you need to have DS Lite support in the CPE. And then the link between the CPE and the ISP network is going to be IPv6 only. There is no anymore native IPv4 support on that link. So what you do is you use this software thing, which is L2TP, to do a kind of tunneling, from automatic tunneling from every customer to the carrier NAT. So this is, yes, somehow still based on carrier NAT. Yeah, but at least you deploy IPv6 here.
So this is basically the same as carrier grade NAT, just more complicated carrier grade NAT, because you need to upgrade all your CPEs, and if you want to upgrade all your CPEs, then choose something that is not CGN, maybe MAP or something.
I am not recommending this. I am not recommending this. I am explaining what is it. The main difference, and this may be key for some ISPs, the main difference between carrier NAT And DS Lite is category NAT don't means IPv6 deployment, while DS Lite is forcing you to move to IPv6. Okay? That's a big difference. Again, I am not recommending DS Lite. I am just saying what has been done. What happens with DS Lite is that you have the, well, that's another difference with carrier NAT. In carrier NAT, remember, you have here a layer of NAT, and here we have another. In DS Lite, you have only one level of NAT, so you break less applications. Okay, that's very important. Now, if we look to what happened in the market in the last few years, there have been some big ISPs deploying DS Lite. That's changing because we have new transition mechanisms that we will see now that are much better than this one. And one of them, for example, is lightweight 4/6, which is like an enhanced version of DS Lite. What is doing?
It's stateful A+P. I'm the author of.
You are one of the authors, yeah.
Of architectural A+P, and basically lightweight 4/6 is this is coming from Deutsche Telekom. Jan Žorž actually developed this, and he took the stateful part of address plus port mechanism and just developed it.
Instead of having here a complete carrier grade NAT, you have a lightweight carrier grade NAT because you put the NAT again in the CPE. If we have CPEs that already have the NAT, why we move it to the network? Let's keep it in the CPE, which is cheaper. Okay? So the network keeps no state. The state is in each box. So if you are thinking in DS Lite, please don't go to this way. Probably there are other better ways. We will see it later. But I will say today has no meaning to go to DS Lite. This is a much better alternative. Okay? NAT64. NAT64 is a way which was meant especially for cellular phones, but not only, to say, let's keep my boxes as IPv6 only, and in the future, I move all the traffic with IPv6. What happens? If you are trying to reach a web server which is IPv4 only, and you have IPv6 only, they cannot talk together. So the NAT64 is providing this translation service between your IPv6 only network and those web servers or services in general that are IPv4 only. Okay? That's the basic idea of NAT64. NAT64 looks very nice, but is based on the support of DNS64. So what it makes is that it creates, it's doing a synthesis of fake Quad A records, so fake IPv6 addresses for those web servers that have only A records, so only IPv4 addresses. So what that means, for NAT64 to work, applications need to use mandatorily DNS. And what happens is that some smart people, including, for example, Skype, originally developed applications using literals. So they embed the addresses, the IPv4 addresses, in the packets. So those applications get broken with NAT64. Okay? So NAT64 looks like a very interesting idea, but actually is not so simple. Yeah, I know.
On purpose.
On purpose.
So with IPv6, Skype loses all the competitive advantage of
Yeah.
other protocols.
Exactly.
Because it's end-to-end.
Yeah.
They are good miners. They have big drilling machines. And all of a sudden, if there is nothing to drill, then, you know, you need drilling machines for
But
nothing.
you know, how many of you use Skype? All of you, right? How many of you have read the Skype license when you say accept? You have read that? Only you. Nobody else.
I didn't read it.
I read it.
You read it.
If you read the license, you will see that you are giving permission to Skype to use your bandwidth, your network, to be a super Skype node. So they can actually use your network. If you and you are talking with Skype, and my network is somehow easier for them, because the peer-to-peer connectivity is not feasible, your traffic will come to my network and then to Jan, and so on. So that's also a security issue. Of course, it's encrypted, but DVD was also encrypted, and many other things have been encrypted. Okay? So it's not nice, especially because, for example, if you are a student in a university or an employee of a company, you are accepting the license in the company or in the university, and you are actually making an unlawful action, because you are saying, I have the right to accept this in this network, and you are not the owner of the network. So Skype is actually doing you to go against law, because you don't read the things. Many people don't read. I started to read when I found all these kind of things. Okay? Now, let's see how NAT64 works. NAT64 some people can say NAT64 is like a carrier-grade NAT box. In some sense, yes. However, there is a big difference. In the case of carrier-grade NAT, you assign a given number of ports to each user. In the case of NAT64, the users have no restriction on the number of ports, because they are getting allocated per flows. Okay? So that actually is much better, even if you still keep a state. But at least it's breaking less and less things. Okay? So somehow we can say NAT64 compared with carrier-grade NAT is a way to do carrier-grade NAT much more scalable. Okay? So if you have an IPv4 only network, NAT64 is not going to help you, because you need to have IPv6 inside to be able to use NAT64. Or if you have literal addresses, it's not going to help you. Okay? However, if you have here IPv6, then it works fine. And you can do the address synthesis in the host, which today most of the cellular phones, for example, already do, for both Android and Windows and Apple. All them do the address synthesis inside. Or you can have an additional box, which is the DNS64 box in the ISP network. Okay? Now, I already mentioned that if you are using applications or even web pages which have the IPv4 address, that will get broken with NAT64. So that's the reason, and this is a list of all the things that get broken with NAT64. And you have things like, we already mentioned Skype, but you have also Spotify, we have Netflix, and many, many other things, Google Talk, many, many other things that in those versions, I don't know if each of those have been updated, but in those versions was broken with NAT64. Okay? So we decided to create a more advanced, somehow, version of NAT64, which we call 464XLAT. 464XLAT is not really a new mechanism. It's not like something new from scratch. It's taking the pieces from NAT64, but solving the problems with literal addresses. Okay?
I have a question.
Yeah.
How many of you are connected to Milutin access points? At least 20 of you. Who noticed that you have IPv6?
After the break, we will do some basic testing.
So I would like to see from those of you who are using IPv6 for the first time now, congratulations, if you see any difference in your current life now. Okay, please continue.
Right, identified by my IPv6.
Okay, so what 464XLAT is doing? 464XLAT is using, as I just mentioned, NAT64, but in addition, it has a small piece of code, is this size of C code, very, very simple, in the CPE or in the device, because actually CLAT, for example, already comes in Android devices. Okay? So what is doing CLAT is solving the problems with literals. And the way it's solving, here you can see it much better. This will be the ISP network. This is an IPv4 destination. If the traffic is going to IPv6, of course it goes straight, no translation at all. But if the traffic comes from IPv4 to an IPv4 destination, it gets translated stateless at the CLAT, which can be the cellular phone or the CPE, and then stateful with the NAT64. So what we are doing is we translate twice, so end-to-end is like nothing happened because we translated once and another one. So end-to-end, there is no translation. Okay? So that's the reason every application works perfectly with 464xLAT, because it don't recognize that has been translated. If you want to see it more detailed, we can see this picture. IPv6 application, IPv6 destination. It goes through, no translation at all. Now, let's suppose we have an application which uses DNS. Even if this application is going to an IPv4 destination, it gets translated only in the ISP by the NAT64. And now we have the Skype case, an application that uses literals. Because it's not using DNS, it requires this translation to make twice, at the origin and at the exit of the ISP. Okay? This is the way 464xLAT is working. Let me skip this one. You can take a look later. I will provide copies of the presentations to Slova, so he can share with you. Yeah. So
it's quite easy actually.
It's easy. The thing is the concept was something like, hey, we have been inventing transition mechanisms one after the other. Why we don't think on this at the beginning? Things happen. It's reality. It's a fact. Why you didn't work it in AP and P before? Because nobody realized it.
Well,
I mean,
I never understood properly NAT64 before I actually configured it in my lab. And when I started configuring and setting up devices with NAT64 and DNS64, and when you implement it, then it's sort of like, oh, that's fairly easy. That's how it works. That thing looks scary complex, but actually when you develop it and play a little bit with it,
it's quite simple.
Lab,
yeah.
It becomes really simple.
Yeah. Okay. So this will be the idea of 464xLAT in a cellular network. Okay. After the break, we will see it in which more detail. But most of the big cellular networks that are deploying IPv6 are doing this way. Okay. Support for these protocols. NAT64 is well supported. CLAT is not so well supported in CPEs, but it's coming. And then you have the DNS, which DNS is supported. DNS64 is supported by any DNS server. So you have Bind and many others that already support DNS64. And then there are already some commercial deployments. Okay, T-Mobile is one of the bigger ones. I wanted to have a demo with CLAT, but because the configuration of the network, we didn't succeed to finish the configuration. Maybe it takes additional 10 minutes, but maybe it's 1 hour, so I didn't want to take the risk to keep you waiting. But believe me, it works. It's being used in very big networks like T-Mobile, and T-Mobile has more than 180 million users. So it means it's the transition mechanism, 464xLAT, that has more users, even if you add together all the others in a single box. Okay? So really, really, really is the way to go. We will talk about this in the next presentation after the break. Map encapsulation. Map encapsulation is basically, you said it before, a stateless DSLite, basically. So with map encapsulation, you have this figure. You keep only one level of NAT in the CPE, and the CPE is doing a kind of tunneling of IPv4 on top of IPv6. That's the E for encapsulation. Okay? It's actually very, very, very close to what you do with Lightwave 4/6, basically. Then we have, I will skip this. If you want to see the detail later, you will get the presentation. Then we have something similar, which is MAP-T. And MAP-T, the T stands for translation. And actually, this is very, very similar to 464X-LAT plus MAP-E. It's kind of mixed between both of them. Okay? The difference in both MAP-E and MAP-T versus 464X-LAT is that 464X-LAT requires a state in the NAT64, while these two mechanisms don't require a state at the ISP. The disadvantage is that these two mechanisms require defining the number of ports per user, while in NAT64 you don't have restriction on that. So it's a balance, it's a decision that you need to take. Now, an interesting thing here is all these mechanisms have not been implemented in cellular networks. So in cellular networks, yes or yes, you only have one option, which is 464X-LAT. Okay? If you have cellular network and non-cellular network, do you want to have two different transition mechanisms, or you prefer to have the same in both of them? Let's suppose you have a CPE with GPON or DSL or whatever, and a backup with 3G. How you manage that if you have two different transition mechanisms? It's not that easy. So having 464X-LAT for both of them makes it much, much simple, even if you keep a state in the NAT64. Okay? That's the difference between MAP-E versus MAP-T. Basically, is the extra encapsulation in map encapsulation, MAP-E. Okay? The rest is exactly the same. There is a web page from Cisco that helps to configure the boxes. So you just put your addressing space and the bits that you want to use for one thing, another thing, and so on. And one way to understand very easily how it works MAP-T and MAP-E is understanding that after the 32 bits of the IPv4 address, you have additional 60 bits of the port. So actually, you are creating a kind of addresses of 48 bits. That's the way to understand these transition protocols.
So
okay?
This is basically stateless A plus B that I wrote the RFC, and this bit I don't properly understand.
It's really complex, but that's the reason why Cisco did that, because it's really complex. One disadvantage of MAP is that basically it's telling you how to do the addressing plan. So you cannot choose your addressing plan because it makes it for you. Which some people will say, well, that's easier. Actually not. If you really are a good engineer, you want to think on your addressing plan. You don't want a box to think on that for you, because it makes some strange things that are not useful later on in terms of routing and so on. Okay? All these transition mechanisms, like DSLite, like Wake, at the end, what happens is that you have millions, if you have millions of customers, you have millions of tunnels in the network, which is an extra overhead in the network. Okay? So it's things to consider versus translation mechanisms like 464X-LAT and so on. In terms of routing, MAP, for example, has the advantage of the aggregation, but it's not perfect. That's what I meant just a few seconds ago with the thing that is making the addressing plan for you. Okay? In terms of performance, there is, I was only able to find this comparison in a Cisco ASR 9K This light is routing the traffic in the ISM blade, and it means 14 gigabits per slot of performance, while map don't need to do that, and then it gets to 240 gigabits per slot. So it's a big difference, okay? And this is almost the last slide. I tried to do a comparison with all the transition mechanisms, a kind of traffic light. So I used green, red, and orange, okay? And then I put some scoring on the top. It's a table not just for checking it now, it's for your reference. You need to readjust the table for your specific case, but in general it works very well for most of the networks. And the interesting thing is that it gives more scoring. I cannot see the numbers from here, but it gives, yeah, for example, I think that's 14. Yeah, and it's the best scoring for 464X LAT. It's just 0.5 difference with map. It's really, really close. But if, for example, you have, as I just mentioned, wireless and non-wireless network, then it's obvious, okay? There is another common question, which is how many ports per user? When you talk about things like DS-Lite or map and so on. And some people say that possibly 300 ports per user behind a CPE is enough. But the problem is that this is very difficult, and it's changing because there are more and more applications using AJAX, and that means they increase the number of ports. And the result is here. You open Google Maps with a small number of ports, and instead of getting the map, you get some blank squares. And if you have a family with, I don't know, 4 or 5 members, using a tablet or a laptop, each of them, this will not be enough. Okay, so in all those transition mechanisms where you have a restricted number of ports, you need to keep updating your network very often. So I don't think that's a good idea. I think it's obvious by preference for which protocol. But really, believe me, it's because I worked with all of them in different business cases and really makes sense. And that's it for the moment. Questions? I don't know how we're going with the timing. More or less? Okay. The next presentation is actually shorter because most of the things I'm going to mention have been already here, so I will skip many slides. Okay? Questions? Nobody? We have an exam later. Okay, so let's get about 20 minutes break. Yeah?